Professor Luciano Fonseca has a PhD in ocean engineering at the University of New Hampshire in 2001, a master's degree in electrical engineering from the State University of Campinas in 1990, and a bachelor's degree in electrical engineering from the University of Brasília, UNB, in 1986. He's an associate professor in electronic engineering at the University of Brasília from 2012 to present, and a member and consultant of the Brazilian La Plaque UNCLOS program, the Brazilian UNCLOS. He was a visiting professor in underwater acoustics at the Éphémère Institute of France from 2018 to 2019. He was a specialist in the Marine Geophysics program of the United Nations Intergovernmental Oceanographic Commission, the IOC in Paris, from 2009 to 2012. He was an associate professor at the University of New Hampshire at CCOM from 2002 to 2009. He was a research geophysicist at the Research Center of the Brazilian oil company, Petrobras, in Rio de Janeiro from 1990 to 2002. And his main lines of research are underwater acoustics, marine geophysics, remote sensing, marine GIS, and scientific visualization of oceanographic data, ocean sciences, and geoengineering. And he's also my dad.
Thank you, Adriano. Thanks a lot. Good afternoon, everybody. It's a pleasure to be here. Thanks a lot for the invitation. I'd like to thank CCOM for the invitation, particularly Brandon and Melissa, who made the first contact, and we were able to book this presentation here. It's always a pleasure, even remotely. No, unfortunately, it's remotely, but I feel that I'm in CCOM at this moment. And I will thank Adriano for the bio, but I would like to introduce myself to you guys just as Adriano's father. Okay, I hope I will not embarrass you, Adriano. Okay, so today I would like to talk about backscatter statistics. The results I will show you guys here were recently published at JASA in this paper that I'm showing here, and my co-authors are Xavier, that you all probably know, né? Xavier Berton, and Rida Fezani, Jean-Marie Augustin, and Laurent Berger. Okay. This research I conducted during my sabbatical leave from 2018 to 2019. I was a sabbatical leave from University of Brasília, where I'm a professor, and I spent the time as a visiting scholar, visiting professor at IFREMER, the Institut Français pour l'Exploitation de la Mer. So IFREMER is located in a very pleasant location. It's here in the westernmost tip of France, here, and it's Bretagne, the province there. And here are my co-authors here. You can see Laurent, Xavier, Rida, Isnaï Buffin is not part of the research, but acquired the data with us. Most of the data that we use for this research, we acquired ourselves in 2017 and 2018. And we use the survey vessel Thalia, a small vessel. But we also use the Celtic Explorer when we went further away in the Celtic Sea, and so in the Biscay Bay and the Bay of Biscay. So this is the location map of our main survey area. We use data from other sources too. I use data from Brazil. I will show you too, and from the Amazon, the mouth of the Amazon. But the main data for the statistics we collect here in the Bay of Brest. You know, see here. This is next door to IFREMER. It was very convenient. And we chose 4 locations. We chose this one here, Elorn, Renard, Olne, and Rascasse. And they have different sediment types. I will show you some photographs and sediment analysis. And they are very flat and uniform. They are perfect for analyzing backscatter statistics. And we surveyed this area with IM 2040, a multi-beam with we imaging 3 frequencies, 300, 400, and 200, 2, 3, 4, okay? And so I will quickly give an abstract of my talk, so help as a guide for the presentation. Huh? I will try to present a methodology for analyzing the backscatter statistics. And for that, we analyzed a huge amount of data from different environments, different depths, different frequencies, and we observe backscatter distributions from different level of processing, from raw data to beam average data to mosaics. So, I mean, different levels of processing. And after analyzing all those data sets, we observed the pattern, you know. If you analyze the snippets data, the raw time series data, we were able to fit a Rayleigh distribution to the backscatter. And if we use the beam average backscatter, one value per beam, we observe a lognormal distribution. And mosaics were Gaussian. So this was our first observation. And then we decided to use a Weibull distribution, because a very convenient distribution, simple with 2 parameters. And finally, we will address the influence of high amplitude scatters, because everything looks fine, but when there's high amplitude scatters, everything changes. And we're gonna, after modeling the high amplitude scatters, I will apply the methodologies to a data set that we acquired in northern Brazil to try to separate the contributions from the substrate and the high amplitude scatters, and so that we could map coral and rhodolites and things like that. Okay, let's go. So introduction to show exactly what data I'm going to use today. No, I will start saying that multibeam backscatter image the seafloor with hundreds of acoustic beams per transmit beam. As we can see in this figure here, no, we have, it's an old figure here, old image here. So you see this transmit beam here, and you form multiple, like hundreds of acoustic beams. No? And in each acoustic beam will record one time series per acoustic beam. So that's what I'm going to show here. So we have a time series here. So the bottom line is that we have thousands of beams, hundreds of beams per beam, and in each beam we have a time series like that. The main processing that we do with that time series is for the bathymetry. I will show you here. I'll take the laser point. It's for the bathymetry measurement. So we take this time series, we do a bottom detection of the rhythm. We see the bottom here. We see the two-way travel time. Of course, the ray tracing, get the sound velocity profile, and you get the bathymetric depth. But this time series we can use also for the backscatter analysis. So the idea is to get the backscatter strength that's coming from the seafloor. Okay, but in order to go from the time series to the backscatter strength, we need to correct the backscatter for all the backscatter distortions. Like you could correct for sonar sensitivity, propagation losses, acoustic footprint, geometry, and so on. And once we obtain this backscatter strength, we can try to correlate the backscatter to the seafloor. I think this is a fun part. You know, the backscatter has a higher correlation to the substrate, to the faces that we are imaging. And so it responds to impedance contrast, to roughness, to volume reverberation, and so on. So we start with this premise that the backscatter is a valuable descriptor for the seafloor, and it helps classification and characterization. Well, the problem is that multibeam echosound acquires a huge number of samples, huge number of backscatter samples. See, in this small area here that we image in Nelorn, one of our survey areas, it's just 500 meters. We image this in like 3-4 minutes, and we image that. And we have 10 million samples, 10 mega samples of backscatter. So this is a characteristic of backscatter. So it's a huge amount of samples. So I just plotted the samples here. I can clearly see a geometric distortion. This is typical about backscatter. You see, this is a navigation. You have very high backscatter at the nadir, just below the vessel. And well, the backscatter gets lower when you go to lower grazing angles. So this is typical of backscatter. Another thing that I see here is contaminated with noise. You have this spectral noise that is intrinsic from the scattering process. A scattering process, you have millions of reflections, you know, with the different amplitudes and phases. When you add it all, you get those statistical spectral noise. And so there are 2 points that one is stressed. When you get backscatter, you have a huge amount of samples, and you have geometric distortion and noise. And we are talking a flat and uniform area. This is completely flat and completely uniform. You can go there with a bottom photograph. So you cannot deal with 10 million samples. You know, you cannot interpret 10 million samples. It's complicated. So you need somehow to reduce the dimension of that backscatter. So there are 2 practical paths that we can follow. One is, for instance, to try to assemble a mosaic. I take all those samples, I average in my filter, I subsample, do average procedures, try to remove the geometry, and get a flat and uniform backscatter mosaic. So this is one step of reduction. Well, I would say a more drastic reduction is to get one number for that area. Like I say, take an average backscatter of the whole area. So this is a main point here in the paper. I get this average backscatter of minus 18.9 dB. So I average all those 10 million samples, and I get that average there. So this is one way of analyzing the data. The other one is to try to get the statistics. Forget about removing the geometry, forget about removing the noise. Just take all the samples that you receive, and you build this histogram here, like an experimental histogram. And you try to analyze the statistics of backscatter. So I want to give credit. We are not the first authors that are working with backscatter statistics. There are many, Cotiros, Jensen, Stanek, Tony Lyons. I don't know if Tony is here. Laurent Lecan, Baudelaire, you know, Demoustier, okay, Penrose, you know, and they try to adjust different distributions to the data. You know, we see in the literature Rayleigh distribution, Gaussian, lognormal. So they repeat themselves in the literature. K distribution, Weibull here, lognormal, K. You know? gamma distribution. So the authors try to analyze the backscatter in different ways. But so it's a recurring theme in the backscatter community. So, but anyway, so we saw all these different distributions here. You know? So we start with an open mind. You know? Let's try to adjust what is necessary in terms of statistical distribution. Although, you know, from my experience, I look at this histogram here, I see a Rayleigh distribution. For me, it's Rayleigh. But anyway, we start with an open mind. Okay, so but before averaging, so one path is to average backscatter. But before averaging, we started averaging, and we are getting different numbers. So I did one average, Jean-Marie did another one, Lohan did another one. So we could not agree in the average. So we start to give a step back. Let's look at the observation, the main observation of the sonar. So the physical observation, okay? So backscatter is basically a measurement of electric voltage there the transducer had, you know, and that voltage is proportional to the pressure that arrives to the transducer. So this observation, this amplitude, it's proportional to the pressure that is arriving there. But the quantity that we want to analyze is called backscatter strength. What is a measurement of energy? So it's proportional to the amplitude to the square, not to the amplitude. So it's the amplitude square. And another point that I want to make sure we agree is that normally we display energy, particularly backscatter, in a dB scale. So 10 log, so we have the amplitude to the square, the observations of the square, and we take 10 log of it. So this is the normal way that we deal with backscatter. Okay, so we take one value of backscatter, and I can square that amplitude, take the log of it, I have one measurement of that backscatter in dB. But my question is, how can I calculate the average of the whole area? How can I average those 10 megasamples? Okay. Well, I'll get just one acoustic beam, just one beam with 32 samples here. And if you look at the first column here, are the amplitudes. You see the amplitude. And the second column here is the amplitude square, to the square. And the third column are the amplitudes in dBs, okay? 20 log of the amplitude or 10 log the amplitude to the square. So we have the three columns. So I propose three ways of calculating the acoustic backscatter. The mathematically correct way, which is this one here. We square all the samples, add them, and take the average. That's the correct way. This is the only way of calculating backscatter correctly, mathematically correct. So you can try to cheat and, okay, average the amplitudes and take the log of the average. This is wrong. Okay, people do that all the time. Or you can take the log, no, you take this column in dBs, so you take the average in dBs, okay, and well, it's already in dB, so you just divide by n, okay? So there are three ways of calculating the backscatter. Simple like that. Well, there's a fourth way too. You can take the median, no? Since we have a even number of samples, the median will be the average of these two here, so 42.1. But so if you look here, you see, if you take the correct average, will be minus 40.4 dB. If you average the dBs, will be minus 42, and so on. So just by choosing a way of calculating the backscatter, you can make errors of 2 or more, okay? So this is serious. This is serious. So just averaging is a source of error. And this is, I would say this is particularly scary, you know, very scary, because the multi-beam manufacturers, they implement such averaging in multiple stages, okay? So even before registering the snippets, for instance, there will be filtering and so on. There's some averaging going on there. But you see, the main average that you can see in the literature is that you have the raw snippets, so the time series, one time series per beam. And then you average and you have one value per beam. Okay, this is one level of averaging. How did they calculate that beam average backscatter? And if you go to the final mosaic, so if you go, you take like commercial softwares that assemble mosaics, there you cannot predict the level of averaging that the data went through. So those 1, 2 dBs, they accumulate in the averaging, so you can distort completely your final interpretation. So, so we observe from the analysis, you know, looking at this axis here, increasing processing level. So let's consider the raw data, the snippets, and then the beam average backscatter. That's the first level of processing, and then the final mosaic from the snippets too. But the final mosaic, one extreme averaging procedure. So you see that we go from a Rayleigh distribution here at the snippets to a log normal distribution here from the beam average backscatter and a Gaussian distribution for mosaics. This is a pattern that repeats itself, okay? And I will show you how it repeats. So here, I like this a lot, you know, so I think the first time I built this 3D histogram was with Yuri Janov. If Yuri is there, hello Yuri. And so I like a lot this 3D histogram. So this histogram is very easy to interpret. So you have the angle here, the angle of incidence. So this is normal incidence, oblique incidence, and here is amplitude, okay? So if you, and the color here is like blue is a number of samples. Blue is few samples, and red and white, a lot of samples, okay? So if you look at this spread of the backscatter here, you see, if you just look at this nice average angular response here, when you see in the papers a nice angular response, you cannot tell that you have a spread like that behind the backscatter. So when we try to look at the angular response with just one line here, no, we are hiding a lot of things. And what I did here is this figure, is try to separate beams from nadir, beams from 45 degrees, and beams from oblique incidence. And you see that the Rayleigh distribution for the snippets, that distribution holds for different angle of incidence. So apparently the angle of incidence does not change the distribution. And if we analyze the beam average backscatter, you get log normal distribution at normal incidence, log normal distribution at 45 degrees and log normal distribution at oblique incidence. So it was very encouraging for us to see that the distribution was a function of the processing level, was not a function of the angle of incidence. Another observation that we did, so we acquired the data with the EM 2040. So we had 200, 300, and 400 hertz. And we could check the distribution for different frequencies, and apparently that pattern holds for frequency 2. So if you change the frequency, you change, of course, the distribution parameters. You have a different average, but the shape would be Rayleigh for snippets, log normal for beam average backscatter. So, well, it was quite difficult to work with 3 different distributions. So instead of trying to adjust 3 distributions, we chose one. So I started working with this Weibull distribution. I remember Brian talking about Weibull distribution like 25 years ago. So, but I like this distribution a lot. It's very simple. If you look at the CDF, it's very simple. It has only 2 parameters. One parameter is alpha, is a center parameter. So B is a center value of the distribution, a mean value, a mode. Okay, so it's related to a center value. And the beta parameter is a shape parameter. So that's the beauty of it. So instead of using 3, I use just 1. So if the beta parameter is 2, I will have a Rayleigh distribution. If it's 2.5, I have a log normal. And 3.6, I will have normal. So this was fantastic, because imagine if I give you a set of backscatter samples, and I do not tell you where it came from. I do not tell you if they are beam average backscatter or snippets, or if they came from mosaic. So you can do a statistical analysis, fit a Weibull distribution. You get the alpha parameter will be the average backscatter, but the beta parameter will tell you if those samples, they came from snippets, beam average, or mosaics. So this was very interesting for us. So we chose this very simple distribution. So our observation, the amplitude, would follow a Weibull distribution. Well, it's not that simple, because the backscatter is energy. So backscatter is amplitude to the square. So the backscatter will follow a squared Weibull distribution. So it was very hard for me to go back to the math and try to, but actually it's very simple. If you create a random value that's square of another one, you just do a variable change and you get distribution. Then I did the integration, and I got the expectancy, the mean of the distribution here. So it's very easy. So, but if you try to use backscatter values in dBs, so that's the complicated one. You would get a log Weibull distribution. So this is how it looks like. I tried a lot to get analytically the mean of the distribution. I could not, so I evaluated it numerically. It's quite easy to evaluate numerically a Weibull distribution. So if you get a set U of random variables, like you can go to MATLAB, use rand uniform, and get 1,000 uniform distributed samples. So if you take the 1 minus the sample, take the log, okay, and then raise to 1 divided by beta and multiply by alpha, you get samples from a Weibull distribution with a center parameter alpha and shape beta. So it's very convenient, very easy. And then I take the average numerically. So it works pretty well. So if you get the backscatter samples, you know, the correct way of calculating the backscatter is adjusting a square Weibull distribution to the data and get the average of the distribution. But, so, this is the correct way of calculating. But intentionally or not intentionally, I do not know, you can try to calculate with the average of amplitudes, or you can calculate with the average of dB values, or you can calculate with the median. So, why I'm doing that? Because people do that all the time. If you look at the literature, people do that all the time. So seldom you see people using the correct way. They use other ways of calculating. So we did simulations. And what is very interesting is that if you calculate in the wrong way, there will be a fixed offset from the right value. So this is interesting. So, and that offset does not depend on the backscatter level. That offset depends only on the shape parameter of the distribution. So that offset depends, the shape is related to the level of processing. So if you see here, the beta parameter of 2 is the Rayleigh distribution. Beta parameter of 2.5 is the lognormal. Of 3.6 will be a Gaussian. So you see the offset depends only on the beta parameter, does not depend on alpha. So we can give like a table, a simple table like that. So if for instance, if you calculate, I give you snippets, you calculate the average in dB. And so snippets are Rayleigh distribution. You calculate the average in dB, you should add 2.5 dBs, so you get the right average. So it's a very simple way of doing a correction and dealing with data that was not calculated in the right way. And so we gave that recommendation in a conference in GeoHab in St. Petersburg in 2018. We gave that recommendation for calculating backscatter. So we see, this is the bottom line, just to recap a little bit. We have 4 ways of calculating the backscatter. You know, this is the correct way, the mathematical correct way. This one is wrong, but if you add an offset, you're okay. Okay, and this one does not follow the same PDF as this one is squared Weibull, this one is Weibull. This one was log Weibull is wrong too, but you add offset, you're okay. And the median, you do not need to imply any underlying distribution because the order of backscatter values, the amplitudes, the square amplitudes or log of amplitudes, the order does not change. So the median you do not need to apply, but the median is not the mean. So there's an offset between the median and the mean. So you need to have an offset too. And well, so these are the good news. So if I come back to that acoustic beam there, that we calculate the beam, the beam average backscatter here, and there's a discrepancies up to 2 dBs. And so if I add the statistical offset, you know, just this column here, the table, I get more or less, well, there's some statistical fluctuation. We're talking about statistics, and it's not exactly. So there's some, give or take some statistical fluctuations, we reduce the uncertainty in the backscatter. So Those are strong recommendations that we give for calculating the average mean average backscatter. So now that we know how to deal with the backscatter, we went back to the bay of Brest and to the four survey areas. So I see in Lorne here, I have the blue lines here are the histogram of snippets. And I'm using for the analysis 300 kilohertz here. So the center frequency there. So I see a Lorne here. It's just a mud. I have some bottom photograph here. And here on Rascas and Renard. So, so a Lorne is a mud, silty sand, gravelly mud, and coarse sand. And we see that the alpha parameter separates perfectly the four areas, okay? So you see the alpha parameter here. So I adjust the distribution and I get the alpha, which is the center parameter. So I get minus 18.9 here, minus 16, minus 14, minus 11. So we could beautifully separate the four areas with the alpha parameter. And then the beta parameter was more or less the same, around 1.9, 1.9, 1.9, 1.9 here. This one here a little low, 1.8. So it's close to 2. So it's close to a Rayleigh distribution. But, well, I was trouble with the high 1.8, you know. What is distorting the distribution towards the exponential distribution? Because exponential will be the beta parameter of 1. So we start asking that question. And so we made an extra observation here is that somehow, so the adjusted distribution is the red curve here. So the experimental histogram are the blue bars. So you see that you have a perfect adjustment here, but here the high amplitude values, somehow there's a discrepancy. A small one, but we can see, you know, so the adjusted distribution goes below the bars of the histogram, you know. So see at the high amplitudes here, there are some discrepancies. And that was a hint why we're getting distortion in the beta parameter towards the exponential distribution, so beta value of 1. And well, I'll just come back here. So before going on, I would like to say some words about backscatter. So using backscatter as a backscatter, I want you guys to regard backscatter as a random variable. So I will make a contrast between bathymetry and backscatter. So bathymetry is very deterministic. In backscatter is a random variable. You see, we see in the literature, we see hundreds of works talking a statistical analysis of bathymetric measurements. But you know, when you do statistical analysis of bathymetric measurement, you are concerned with errors on the measurement system and the positioning system, not in the bathymetry itself. Because bathymetry is a deterministic variable. Let me explain. Imagine that you have a perfect ruler, perfect, zero measurement error. Our perfect ruler will be this lead line here. So you go there in one place, you measure the bathymetry. If 25 meters. If you come back at the same spot and measure with that perfect ruler, you're going to have 25 meters and that's it. Because it's a deterministic variable. The error will be in the measurement system. If my measurement system is perfect, my positioning is perfect, I will not have any error in the bathymetry, unless the environmental change. So there's a current there that brings sand and change the bathymetric path, okay? But So bathymetry is deterministic. So imagine that you have a ruler to measure backscatter to, and that ruler is perfect too. That ruler will not be like a lead line, will be like dice, okay? Not just one dice, will be like a 6-sided die for Elorn, an 8-sided to On, a 12-sided to Ruskas, and a 20-sided to Renard. Okay? So you go there with that perfect ruler and you measure. To measure, you roll the dice. So you roll the dice to get a number 2. Okay, I'm happy with 2, backscatters 2. I come back tomorrow, I roll the dice and get 5. And so I say, well, I cannot trust backscatter. Backscatter has a huge variability. What is going on? Yesterday I measured 2, now I measure 5. So, well, that's perfectly fine. It's a random variable. You can get numbers from 1 to 6, okay? Well, it's how it's built. But imagine that I roll the die and I get a 5. And I ask you, because I'm concerned with seafloor characterization, did that 5 come from Elorn? Did it come from Ol? Did it come from Raskas? Or did that 5 come from Renard? I just cannot tell. I can get a 5 here, I can get a 5 here, I can get a 5 here. But if I roll the dice many times, like 50 times, 100 times, and I get the average, and if the average is close to 3, I will say, well, those samples, they came from Elorn. If the average is around 10, I will say, well, those samples come from Renard. So the bottom line is, you cannot analyze backscatter values. You have to analyze parameters from the backscatter distribution. This is the only way of getting reasonable results from it. Well, so far everything looks okay, perfect, mathematically correct, but there are always problems. And we observed in the Bay of Brest and many places that we were surveying there, that the seafloor, the acoustic samples, the acoustic backscatter samples, they are contaminated with noise, and pretty often we got some what we call high amplitude scatters. And it's very easy to see where they come from. Imagine that you have like this bottom photograph here, you have like a sandy seafloor here, like sand. And I call that sand the substrate. Let's see. So we have that sandy substrate there, and you image, you get a backscatter values, you average them. But imagine that you have high amplitude scatterers. What is that? Some pebbles, shells, point scatters, they are there. So when the acoustic wavefront hit those high amplitude scatters, you get a very high value in the backscatter. So you get kind of outliers in your distribution. So you can treat them as outliers, or you can treat them as data, because actually it's giving some information to you. So if you have those outliers, you do not have this seafloor here without pebbles and shells. You have that one. Okay. Well, so this is interesting, but if you have high amplitude scatters, that 4 approaches for calculating the average backscatter will fail. That's a huge problem. And I see, well, and I come back here just 1 minute, and the high amplitude scatters is not the exception, it's the rule. You always find high amplitude scatters. You have like We can talk about percentage of high amplitude scatters. If you have like 1%, it's a low percentage, but you have 3, 4, 5, no? So it's not like an exception that I'm talking about. It's a rule. So let's come back, return again to our beam. So I have our beam, I have 32 samples. That we calculate in different ways. We added offset, everything looked okay. But now I will add just one sample with high amplitude. The last one here, okay? This blue. So I will take 30, I will add one high amplitude scatter. You can say, this is an outlier? No, this is data. It came from a high amplitude scatterer, okay? And when I take the average backscatter in the right way, averaging the squared amplitudes, I have minus 18 dB. If I use the amplitudes minus 29, here minus 37, you see just one sample of high amplitude scatters destroyed completely. Basically, these two here, you cannot trust this one and that one. That's why people do not use it, you know, they just abandon it. You know? It's the correct way, but if there is a high amplitude scatter, it will destroy completely, because it's an unfair average. You know, you have the substrate and you have the scatter. This minus 18, okay, does not reflect neither the substrate, neither the pebble there. So it will be something in between that does not mean anything. Okay, so those approaches they vary by, you see here, like 20 dB. So it's unbelievable. Okay. So in order to analyze that influence and model that influence of high amplitude scatters, we start with this histogram from that area there. So the black bars are the experimental histogram, and then the blue line here, the blue line will be the underlying PDF. Will be Weibull distribution with an alpha parameter and a beta parameter that reflects this experimental histogram here. Then I will add like some random noise, 20 dB signal to noise ratio. I will add some noise. When I add some noise, I will go from the blue one to the red one, and then I will add some high amplitude scatters, and you see here the presence of the high amplitude scatters here in the modeling. And in this case, I put 1% of high amplitude scatters. So with that in mind, I did this statistical simulation. So we start with a seafloor that could be modeled with a beta alpha parameter, center parameter 0.01 is minus 40 dB here. Minus 40 dB. And beta parameter of 2. So we're talking about snippet samples. Then we add minus 20 dB of random noise and 1% of high amplitude scatters. That's it. And then we made simulations for various number of samples, like 10, 20, up to 100 samples. And we calculate the average using the amplitude square, which is the correct way, the dB, the black line, the median, the blue line, the average of the amplitude is the green line. So we see here that with 1% of high amplitude scatters, you cannot trust at all the average calculated with the amplitude square. The values vary by 20, 25 dB. It's completely unreliable. You just forget it. You cannot do that. If you use the amplitudes, the green line, so you have discrepancies here of like let's see, 18, 20 dB, it's wrong too, so it's unreliable. If you take the backscatter, the average in dB, which is wrong, okay, of course I'm adding the proper statistical offsets here. So you get the black line. So if you have a lot of samples, it's pretty acceptable. If you go to like a lower number of samples, which is the case of a beam average backscatter, so you can have discrepancies of 2.5 to 5 dBs, could be pretty wrong. It's unpredictable too, it's completely statistical. Well, but if you look at the median is pretty reliable, okay? You get around minus 40 dB regardless of the number of samples, no? So the only reliable way of calculating the beam average backscatter is with the median in the presence of high amplitude scatters. So with those observations, I would like to give you guys some recommendations. No, the direct averaging of squared amplitudes, no, should be avoided. Never do that. You see, this is the red one here. The results will be contaminated by noise and high amplitude scatters. So you cannot do that. Averaging amplitudes, okay, it is neither good, you know, you can have huge distortions, is the green line here. You on top, it does not follow the same PDF density function as the PS, so you need to add the statistical offset. If you average dBs, well, you have problems if you go below like 20 samples with the case of beam averaging snippet samples. But at least it's limited. It seldom goes beyond like 3 dB. So I put 25 with an average here. So it's pretty, but that distortion is statistically unpredictable. So we recommend approach 4, that's calculating the median and adding the statistical offset. Well, so let's see some comments about adjusting Weibull distribution in the presence of high amplitude scatters. No, the median is a very robust estimator, okay, for the alpha parameter. So if you get the median, notice you get the alpha parameter. Even with fewer samples, we could still get a reasonable estimation from the central value. So it's okay. Well, but using the median, you know, if you use the median, indirectly you remove the outliers. So you remove the contribution of the high amplitude scatters. So when you get an alpha parameter from a distribution using a median, you get something that reflects the substrate, not the scatters, okay? This is a very important point. So, okay, but once the substrate has been defined, okay, I made in the statistical analysis, I removed the outliers, which are the high amplitude scatters. I get the substrate. Now that I define the substrate, I can see a difference between the observation, which is this histogram here, those bars, and the adjusted distribution, okay? So that difference here is clearly related to the distribution of high density and distribution of high amplitude scatters. Okay, this is the point here. Well, a quick point about the beta parameter. Beta parameter is more difficult you need more samples to have a reliable estimation of the beta parameter. And it's in the presence of high amplitude scatters. So if you do not have high amplitude scatters, so if the substrate beta and estimated from the data, you get a line here. So if you start with 2, you end with 2, and then that's the expected one. But if you have like 1% of high amplitude, if you start with 2, you end up with 1.8. So when you have high amplitude scatters, point scatters, the beta parameter from your distribution will go towards this exponential distribution, will be lower than 2, okay? And somehow you can try to account for that distribution and density. So that's why I introduced here one extra parameter with this delta. It's not a parameter from the distribution. It's just the difference here between the histogram and the adjusted PDF. So to test those ideas, we took some data here from the mouth of the Amazon. They were acquired by the Brazilian Navy trying to map the Brazilian coast for the extension of the continental shelf. And so this is a location map. So this is the French Guiana here. So the Amazon River. So this is the mouth of the Amazon here. So I will show you some data from this area here, figure 12, and then figure 13 here. Okay, and so this was the area that was mapped in this project. We mapped the whole Brazilian coast, okay, with some track lines here, like following a seismic lines there. Okay, so I use this data for this analysis. So in this data, I concentrate in an area that I had a map, node map, showing coral here. So that this map is blue, is like a sandy sediment, you know, okay. And this orange here is like coral. So this was a node map. So I tried to get a survey line there. It was a EM 710, 90 kilohertz. Okay, so it was mapped in 90 kilohertz, and I see, I like it a lot. There's a perfect boundary here, you know. So you have A here, one faces, and B another one. So it was a perfect match. So what did I do? I got the histogram here of the A area. What do I mean get the histogram? I get all the samples that came from area A, regardless of angle, ping, beam, you know, I put all the samples there from snippets and made a histogram. So I have this histogram A here. So I take the samples from B and I get the second histogram. So I can see a difference in the alpha parameter, it's expected, minus 22, low backscatter here, minus 15 there. But what is really interesting is the beta parameter. In B here, the beta parameter is 1.9. Well, very close to Rayleigh. Okay. I do not, using my logic, I do not expect the presence of high amplitude scatters. But if I look here, there's a huge distortion, 1.55. It's close to exponential distribution. And then, so if I calculate the delta parameter, just the difference between the adjusted PDF and the histogram at the high amplitude values here, I get 2.9%. In here, 0.4. So in this case, the high amplitude scatters, you're related to the presence of coral. okay? So this was, for us, it was fantastic because I could run the simple algorithm, okay, in the whole area here, the whole Brazilian coast. And I could get a first map of maybe there's coral here, there's not, just by mapping the beta parameter along track. So this was our first example. The second one is here, no, closer to the French Guiana, is an area here. The depth here is approximately 100 meters. 100 meters. It's on the continental shelf before the slope, just before the slope. So in this area here, so it's an area there was a node map there telling there was rhodolites there. Rhodolites are like it looks like coral, but it's round, yeah, okay, primarily composed of algae, you know. This is how they look like. Actually, these photos are from that area. You see, you have rhodolites here, they're spread, and you have like mounds of rhodolite here, okay? So that's what you see here. You see the mounds here, see? You see this speckle here, this spread rhodolites. Yeah? So if I look at this acquisition line here, I will show you 1, 2, 3, 4, 5, and 6. You see different densities and distributions of rhodolites in this backscatter image. And then, well, I see, let's adjust our Weibull distribution there. So for each area here, the gray bar is the observations, all the samples from that area, regardless of angle of incidence, beam number, and so on, pink, and so on. And the black continuous lines is the adjusted distribution. And so here you see in this table, for instance, they all have a pretty similar alpha parameter. The central value is pretty the same, -20, -20, -20, -20, -19, -19.6. So the alpha parameter is basically the same for the 6 areas. So the substrate apparently is very similar. But if you look at the beta parameter, it changes. It is very low, 1.87, 1.81, 83, 82, 80. So this beta parameter is probably related to the density and distribution of rhodolites. In this case, the point scatters are the rhodolites. Okay, and if you look at the delta parameter, which is the difference here between the histogram and the adjusted PDF, you have 4% here. So it's the maximum amount is this one here. Okay, number 5. Okay, this one is pretty high too, number 6. And the others are like 2.5, 2%. So if you look just at the backscatter, okay, if you look at the backscatter mosaic, you're gonna tell this is high backscatter, this is low, but the substrate is the same. The difference is in the density of high amplitude scatters. In this case, rhodolites. So it's in mapping rhodolites, it's very important for mainly here in Brazil. So we are running a project offshore Rio de Janeiro for a wind farm, and the main point for using multibeam there is to avoid areas with rhodolites, because you need to protect them. So there's an environmental risk in finding rhodolites, so it can destroy completely a project. So using that statistical analysis is helping us avoid rhodolite areas. Okay, I'll draw some I'm talking too much, and I just wrap up with some conclusions. So that, and Let's see, acoustic backscatter, if properly processed and interpreted, it's an important source of information for remote seafloor characterization. So I strongly believe in that. You know, I spent my whole career talking about that. But for that but it's important to stress, okay, that the acoustic backscatter is a random process following an underlying PDF. So if you do that, you have this satisfactory match between your backscatter analysis and the substrate and the seafloor. Okay, it was observed that the raw, so here, no, we could separate beautifully the four areas here. It was observed that the raw unprocessed time series follow a Rayleigh distribution. That beam average backscatter, one value per beam, follow a lognormal distribution, and the mosaics follow a Gaussian distribution. That behavior appears not to be influenced neither by the angle of incidence, neither by the frequency. So we propose a two-parameter Weibull distribution that has a center value alpha, which related to the mean backscatter, and a beta parameter is a shape parameter that's related. If it's greater than 2, it's related to the level of processing, just like here. If it is smaller than 2, it's related to the presence of high amplitude scatters. You see, all the processing stages, the right way of calculating the backscatter is this. You take the average of the amplitude square. And so if we calculate by a different way, there will be discrepancies, okay, of course. But if you add the statistical offset, you'll be okay. You remove those discrepancies. But but the shape of the PDF and those parameters will be completely distorted in the presence of high amplitude scatters. Okay. And so if you take the average backscatter in the presence of high amplitude scatters, the average that you get will not relate neither to the substrate nor to the scatters. There will be something in between that you can draw any conclusions. So we suggest in this work a way of separating those two contributions, like separate the substrate from the high amplitude scatters. So with the proposed method, we could separate the two contributions and detect the presence and the spatial density of scatters with the delta parameter. The parameter alpha of the adjusted distribution relates to the mean backscatter. So if you want to have the mean backscatter on area, the elegant and correct way is to adjust a Weibull distribution and take the alpha parameter. The beta parameter relates both to the presence of scatters, if the value is lower than 2, or to the level of processing, if the beta parameter is greater than 2. Okay, so if it's 2.5, you have beam average backscatter. 2.6 is mosaic, 2 is snippets. 1.7, you have like snippets contaminated with high amplitude scatters. Finally, the delta parameter can conveniently quantify the level of contribution of scatters. So I apologize for extending myself, and so open to any question. Thanks a lot for your attention.
Any questions from Brad?
Yeah. Good afternoon, both. My name is Miguel. Thank you for the presentation. So I was wondering if when you calculate your delta parameter. Do you use the full histogram or just the tail of the histogram?
No, just the tail. So we define high amplitude scatters as something that's around minus 5 dB. Okay, so I take something minus 8 to around minus 5 dB. So that's what we're looking. So just a tail of distribution. So when I talk minus 5 dB, you have to convert to amplitude to see exactly where it goes in the histogram, you know, because the histogram, we always display the histogram in amplitude. This is important, okay? It's not correct to display histograms in dBs, but when you display a mosaics, you use dBs, okay? But if you look at the overheads, every time we show histograms, we use amplitude, which is the random variable.
And when you, so as a rule of thumb, would you suggest to always get an average of the backscatter by using the median and the statistical offsets in order to avoid the influence of the high amplitude scatterers?
Well, see, it's because there are two things here. One is the recommendation to calculate the average backscatter. So we strongly recommend that you use the median, okay? Median. But be careful. When you calculate the median is not the mean, okay? To go from the median to the mean, you need to infer somehow the distribution. So if you do not want to adjust the Weibull distribution all the time, you can use that simple table. If you take the average, if you take the median of snippets, you add one value. Okay. If you take the median of beam average backscatter, you take another one. And if you take the median of samples in a mosaic, there's another offset, you know. If I remember, for mosaics is 0.4, for beam average 0.4, for snippet is 1.6. Well, what is there in the table? Okay, so that offset table is a shortcut. Okay, because 99% of the time we're dealing with mosaics, beam average backscatter snippets. So it's Rayleigh, lognormal, or normal. Okay, so this is one point. But when you adjust the distribution, okay, since you're using the median, when you adjust the adjusted distribution will reflect the substrate. So somehow you remove the outliers, which are the high amplitude scatters. So if you have the substrate, you can infer something about the high amplitude scatters using that trick that you point out to see the difference in the tail of the distribution, just like you said.
Thank you.
I have a question about the residue. Can the shape of the residue or the distribution of the residue be used in any way to classify the scatters, the high amplitude scatters? For example, could you tell apart a coral scatter from a rhodolite scatter? And also, is the shape of the scattering? You said that the density, the delta parameter, showed up independent of frequency. But does the shape or the value of delta vary with frequency in a way that can be used to characterize the scatters?
Yeah, I will try to share the screen here. So, okay, okay, so you're talking about those histograms, is that true?
Yeah.
So if you're asking if the shape of the table, the tail here, has some
Shape.
information on it. Yeah, that shape. No, we did not analyze that, you know. So at this point, I was only concerned about, you know, that difference here. You know? The amount of samples, they are above the adjusted distribution, okay? So I consider them, so that's why I came with this simple delta parameter. I got, just like I was counting those samples here and divided by the total number of samples. I see like I have 3% samples that are outside my my fitted PDF. But I think could be interesting to see the shape of the table, the tail, the shape of the tail can have some information there, but I did not look into that.
I just had one last question. I'm wondering if when you were mentioning how bathymetry was deterministic, whereas backscatter was random.
So it's a little bit distorted. Can you repeat, please? I did not get it.
Regarding how backscatter is inherently random, whereas bathymetry was deterministic.
Yes.
Can you elaborate on some of the sources of what makes that backscatter random?
Well, you see, I don't understand completely your question. I think you're talking about that. You see, well, I'm trying to advocate this, that backscatter is a random variable, okay? And in most of the distortions that we see in the literature are related to a wrong way of calculating the beam average backscatter and not treating it properly as a random variable, okay? So that's why I came with that image. If that image of the rolling dice is okay, so the dice is perfect. So there's no measurement error. It's 1, 2, 3, 4, 5, or 6. But every time you roll, you get a different number. You need to, so if you get, I roll a dice, I get 2, I cannot characterize the dice, okay? I cannot. To characterize a random process, I need the distribution. A value of backscatter does not mean anything. You need a sufficient number of samples so that you can draw conclusions about the shape and the parameter of the distribution, regardless of the distribution that you're dealing. You know, we are proposing a Weibull that fitted pretty well, but I think that the right way is to use the parameter of a distribution, not the values itself. And be careful in the way you calculate, you know, the consequences of using medians, means, average, mean of square values, square amplitudes. You need to go back to the basics of the observation so that you can calculate it properly.
Okay, thank you. And can we give him one last round of applause? Thank you guys for coming and staying around. If you're in the seminar class, remember to sign that sheet on your way out. See you next week.
Luciano, can I ask you a question?
Of course, Brian.
I actually have a couple of questions. The first one is, well, the first thing is, I love the clarity of the description of what you're doing here. I think it's something we've been badly missing. So this is great. When you're looking at using the median to robustify your estimate of central location, do you think there's any value in other robust estimates of locality, or is the median giving us as much as we need to do something useful here?
See, to be honest with you, I tried other approaches too. Okay, I tried, for example, removing 10% of the lower values and 90%. So take the 1090 mean. Okay, but it did not help at all. See, it was the median. Well, to be honest with you, the easiest way is to use the median. There are other possible ways. The drawback is that in order to get the median of a set, you need to order that set. Okay, so we are talking about getting the median from a Lord, that small area there. I had 10 million samples. So it's, well, if you want to order 10 million samples, it takes some time, you know. So
that's why I was asking, because it can be expensive. Yeah,
it can be very expensive, but you see, there's a shortcut for that. So, for example, if you assemble, instead of ordering the observation, you assemble a histogram, and you get the median from the histogram. Okay, so that's very easy and very direct. Computationally, it's not expensive. So we always work with the histogram. You get instead of using the samples itself, you get the histogram and you get the parameters. The median you get directly from a histogram. Okay. Just like counting, you count the bars. When you get half of the samples, you get the median. So that was the turnaround. So we're almost quitting the idea of using the median. So, well, we'll use the histogram. So,
the other question was, when you compute your shape parameter and you indicate that it's greater than 2, so you think you have or less than 2 rather, than you think that you have outliers. Do you think that would be a good indication that you should consider a more complex model? Meaning that, if your argument is that the correct distribution is basically the substrate, and then the deviation from that distribution is I'm seeing some scatterers on top of that substrate. Would it be worthwhile considering a model where you'd say, well, there's actually 2 models here. There's the bit for the substrate and the bit for the scatterers, and what I'm seeing is the combined version of that, and I should try and tease those apart and give me some better descriptive capability? Is it valuable to do that, or is it just you're going to gain nothing much more?
Well, Brian, I think it's valuable. You see, I was trying some annealing, so you get 2 distributions and try to add those to Weibull distributions, so that you have a Weibull distribution with an alpha parameter for the high amplitude scatters and a low one, so you can adjust. So Adriano helped me with that, and it works pretty well. But I think it was too complicated. So I was not confident that I was creating artifacts. In this first approach, just to adjust directly the distribution and see, okay, this difference here in the high amplitude scatters is very easy to see. So for first approach, I think it was okay. But I think the right way, you see, there was one suggestion from, I don't remember who asked that question, that the shape here, the shape here somehow is related to the, for example, you see, so you can have high amplitude scatters around -5, -6, so it somehow changed the behavior here, but well, it was a first approach. I think some optimization, trying to use 2 distributions and see the best fit will be better. Okay, and we plan to.
Yeah, it's always a question of whether the extra explanatory value is worth the complexity of putting together an unmixing algorithm of some kind. It's always a
yes.
I like that it's simple here.
Yeah, the simpler normally is
Usually a better option.
A better option. I see. So I was not trying to quantify perfectly the density of rhodolines, See, I'm tempted to say there's 1% here, 2%, but but I the only thing I will claim at this moment is that here I have more than there, more or less twice the density.
Yeah. Hopefully next time you come visit us in person and we can have a quiet sit down with a pint or some whiskey and talk about this in more detail. I'm really looking forward to it. It's lovely to see you again.
Love to see you again. Right. Bye-bye.